Hello, discrete math fans. Let's talk about our second form of indirect argument called argument by contraposition. Now, some people would say that this really isn't an indirect argument. It's really a direct argument form. But the book lists this as part of their indirect argument, so we'll just roll with it. I don't think it really matters very much whether you call it an indirect or a direct argument. There's no question at all that proof by contradiction is an indirect argument. This one, maybe it straddles the line a little bit. Now, the argument by contraposition is based on a logical equivalence between a conditional statement and its contrapositive. Remember that if you have a statement form, P implies Q, that's logically equivalent to its contrapositive, not Q implies not P. So now, to prove a conditional statement by contraposition, what we would do is take the contrapositive of the statement, prove that contrapositive by a direct proof. Aha, see, direct proof, not necessarily indirect. And then we conclude that the original statement is true. Let's outline the method of proof by contraposition. All right, first thing we do is express the statement that we want to prove in this form. For all x and d, if p of x, then q of x. So really, we need to have a conditional statement. All right, second thing we're going to do is rewrite this statement in the contrapositive form. For all x and d, if q of x is false, then p of x is false. Now, very often you can do these two steps in your head. You don't necessarily have to write these things down. Sometimes it helps for clarity to just write down what these statements are. And now we prove the contrapositive using a direct proof. So part A, we suppose that x is an arbitrarily chosen element of D such that q of x is false. And then we have to show that p of x is false. All right, that's the outline of the proof method. We'll come back and work a few examples involving proof by contraposition. Okay, that's all for now.